Exactly. I mean, thank you. Well, today we start a new topic in this class of general physics at the University of St. Joseph. We start with electricity, magnetism, which for a long time was believed to be two separate phenomena. Electricity and magnetism were studied independently first. And it came out after so many years that of research and coincidences and observations that people realized that the two phenomena are related. And it was Maxwell who consolidated this theory, the theory of electromagnetism. But of course, Maxwell had not been possible if Ampere, Biot-Savart, all these guys in the past had not done this tremendous job. No? So the achievements in a science are like that, little by little, step by step, and suddenly becomes somebody who comes out to be the hero. But I think the heroes are everyone, because without these small steps, Maxwell had not consolidated. Interestingly, Maxwell theory is Lorentz invariant, and Lorentz invariant means that, well, Lorentz symmetry is the symmetry of a special relativity, for example. So it came after Einstein. Remember, Einstein realized that the symmetries of the Maxwell equations are the right ones. And instead, the Newtonian mechanics is the one who had to be changed. So that gives a special relativity, but we will not talk about special relativity here, maybe later in this class. First of all, electric charge. I have to say that it's by convention. We assigned some labels to the charges, positive and negative. But it could be perfectly yellow or red, blue, whatever. It doesn't matter. The point is that there are some labels assigned to the charges. We assign positive to those charges which emit electric field. So it means if you put a test particle here, positive, with a small charge, it has to be small. The charge here has to be much smaller than the charge of the source for not affecting the field, because this is a potential source of field. So it gets repelled. So it means this charge feels a force going outside, proportional to its charge times the electric field. In contrast, if you put a negative charge, it happens the same. Yeah, the same, but in opposite direction. You put a test particle positive, and by convention, the electric charge, the lines of the electric field enter. So this particle, being positive, will feel attraction. And of course, by convention, we take the electric field in the direction of the test particle. That's how the lines of electric field are designed. There are experiments in the laboratory. I don't know if we have the equipment here. Later we will see how these things can be done in the lab. But for the moment, this was purely conventional. We could have said that this is negative and this is positive, and the theory doesn't change. I mean, positive or negative, it doesn't matter how do you define, but once you define the electric charge as one of the labels are positive and the other as negative, you have to keep it consistent, you know. So later we will study electric field and how the dipole and these kind of things. But for the moment, let's go and let's analyze what these notes have to tell us. As I say in a moment, there are two kinds of charges, positive and negative. Opposite charges attract. That's why you see this figure, positive and negative. If I put a cable hanging some positive charge and a negative charge, let's assume that they have the same charge in magnitude, but opposite sign. They will attract sign. Equal charges, they repel each other. So from the perspective of this charge feels a force in this direction. and vice versa. This charge feels a force in this direction. Let's put Fe as electric force. No? In this case, it's different. This charge feels a force inside, and vice versa. This one is a couple of action-reaction. No? So if you make a free body diagram for this, let's isolate this charge, the positive. Let's put it here. It will have a tension in this direction with some angle. It will have the electric force here. And of course, its weight, the gravity, mass of the charge multiplied by gravity. These are the forces acting on it. And then you can assume in X and Y equilibrium, the sum of forces is equal to 0. And you can solve any problem in that way, depending on information provided. Something important, and I will remark it later, is that the charge is quantized. So the electric charge is quantized. What is quantized? It means that any body, we can charge any object, but the total charge will be a multiple integer of the charge of the electron. So it means the total charge of a body, is Q equal N, which is the number of electrons times the charge, the magnitude of the charge of the electron. So you can guess how many electrons are in an object by knowing its charge, or how many electrons are missed in an object. Let's say if an object, the electrons escape from the object remains positive because the electron has negative charge. Then, of course, it's positively charged. The opposite, if the electrons come to the object, it charged negatively. Why the electrons? Because the electrons are the particles which are easier to remove in the atoms. Let's say you have an atom. Remember the picture of the atom is from quantum mechanics, the first class we gave here. You have the nucleus. You have a nucleus here in the center, very small, with protons, neutrons. A pool of protons, they have positively charged. Positively charged, but they should be repaired, via this condition, but still they remain together because the strong interaction is keeping them together. The strong interaction is stronger than the electromagnetic interaction. But at the same time, you have an electrons here, which are not particles, they are waves. Quantum mechanically, the electron is perceived as a wave, an electronic cloud here, with some peaks of probability. So you can guess the probability of finding the electron somewhere. But when you inject energy to this atom, the first particle which will move is the electron. The metals, let's talk about the metals. Why the metals are good conductors? Why you shouldn't touch a metal during the rain or so? They are good conductors. Why is that? Somebody can tell me? Electrons. Exactly. The electrons are free. Actually, there is a layer of electrons moving freely in the metals. That's why they can conduct electricity. The electricity normally is transmitted by the motion of electrons. The electrons move in one direction, the current moves in the opposite direction. Because negative motion of charge in one direction is equivalent to positive motion in the opposite direction. This is what happens. Now, for example, a ceramic or this table is a bad transmitter of electricity, let's say. It transmits electricity in a very bad way. It still transmits a little bit, but why is the case? Why do you think? Because the electrons are more attached to the atoms in that material. They cannot move that freely. Maybe there are eventually a few electrons who can escape and so on, etc. Depends on the voltage. Later we will define what is the voltage. The voltage in advance, I can tell you that is the work done by the electric field. Is the work. We study work here. And in analogy with fluids, it will be like the pressure. Let's say the electricity flows from high voltage to low voltage. The water flows from high pressure to low pressure. Remember that. The heat in thermodynamics flows from high temperature to low temperature. always like that. So these three phenomena are analog in that sense. And it comes out by chance, not by chance, actually it's not a coincidence, there is a physical reason for that, is that the metals are good transmitter of, they transmit very well electricity, they transmit extraordinarily well electricity, but also heat. And the reason is the same, because the transmission of heat also is done through the motion of particles, in this case, electrons. So let's continue a little bit. I extended a little bit the story here, but it's important to remark. This is the picture of an atom, typical atom. This is what I was talking about. When you introduce some voltage, the first particle to escape is this. For removing the protons, and you need that extraordinary huge force. So with this voltage, ordinary voltage, you will not do it. The electricity, as you can see, is transmitted a cable. When you see a cable, any cable, the cable in that cable you can see there is connected the laptop, contains positive and negative charges. Normally it's neutral. The positive and negative charges are the same amount. So that's why even if you touch it with naked hand, you will not feel anything. However, if you apply a voltage, let's say voltage 1, voltage 2, with the voltage, this move for voltage 1 larger than voltage 2, it means the current will move in this direction, and the electrons will move randomly in the opposite direction. But the velocity of the electrons is very small, very ridiculously small. You will calculate later, because they collide. They have, when they are in the material, they have to collide with many collisions, and they release heat. That release heat. That's why the cables get hot. That's why the equipment gets hot, because of these multiple collisions of the electrons with the atoms, impurities, whatever. Then somebody can tell me, and this is a question, actually, I remember my professor in Universidad del Norte, when he always asks this question, why when you switch on the light, for example, if the electrons move so slow, why the light instantaneously appears here? I mean, when I switch on the switch, when I switch on, I am sending an electric field which flows because of the difference in voltage. And the electrons start to move. Well, why, if the electrons move so slow, the light appears instantaneously? Anybody can guess, can tell me? No idea? You can guess, you say whatever. That's one issue. That's one issue. Of course, there are electrons also here, near here. There are electrons there. They are very far away from each other. Once you switch on, these guys here also start to move. They are close. But what is the signal that moves quickly? I mean, which signal tells to this electron, you have to move, guy? Move, or I kill you, or something. Is the electric field. The electric field moves at the speed of light. Move at the speed of light. So the same speed of the gravitational waves and many other particles, because something you should know, and normally in the high school they don't tell you. Sometimes the students get confused because I say things which are advanced, and they say, no, in the school we didn't learn in that way. Well, because in the school your teacher doesn't know that. That's the only reason. But the electromagnetic interaction is mediated by photons. It's mediated by photons. So photons are the propagators of the electromagnetic interaction. The gravitons in gravity, etc. Whenever a particle is massless, it moves at the speed of light. It doesn't matter which. You will never be able to move at the speed of light. Me neither. You neither. No one of you can move at the speed of light. Not even if you try. Not even if you have an infinite amount of energy and force, because we are massive. And the only, it's precisely for the fact of being massive, we can never reach the speed of light. But the electric field moves at the speed of light. So once you activate the switch here, the electric field comes here and gives the signal immediately, move, electron, move. And then the light switch on. That's what happened. You have a question?
I just wanted to ask in regards to the electron getting from
Sorry, can I increase the voice because I cannot.
the graph that you had before of the electron getting pulled from the atom. Isn't that just the photoelectric effect?
Also, let's say there are two ways. There are two ways to move electrons. That's another way to move electrons. There are two ways to move electrons in a material. One is by applying a voltage, and the other is applying light. That's the photoelectric effect. That's a good question, actually. But not all the materials experience that property, because for the photoelectric effect to be effective, that material in particular needs to satisfy a series of properties. Probably the electrons have to be more loose in comparison with this. I mean, there are some special characteristics of those materials for that to appear. But it's true that the light can also. And in such a case, it's a photon hitting the electron and so on. When we reach quantum mechanics, because we haven't reached quantum mechanics, we will learn quantum mechanics here, but basic, not advanced, because of course we don't have time. There's not enough time to analyze, to study advanced quantum mechanics in this class. But what I can say is that you are right. There are two ways to release electrons: difference in voltage and light, the photons. Remember that the light is a bunch of photons, is what quantum mechanics tell us. And each photon hits electron and it has to release. But if the photon doesn't have enough energy to release the electron, because there is a bond energy. Let's put you have the material. This electron here has a bond energy. If the photon coming here has less energy than the bond energy, the electron will never move. The photon needs a frequency high enough such that it has high energy in order to defeat the bond energy and release the electron, and the electron will move. This is the principle of the photocells, the solar energy, and so on. This gave Einstein the Nobel Prize because he was the first guy who explained in a satisfactory way this phenomenon. Before any attempt to explain the phenomenon classically failed. You have to use quantum mechanical arguments, and it was thanks to Max Planck, who was the first guy who realized that you have to quantize energy, because of the catastrophe, ultraviolet catastrophe, which we will learn later, actually. Well, because if I go back, we will extend so much. But you should. This is an example of how science progress. First, Max Planck realized you have to quantize the light in order to reproduce the black body spectrum. Then Einstein said, I can use this idea for explaining the photoelectric effect. That's why it's important to read papers, especially the most advanced papers, going to the board, going to frontier, and every day be aware. For example, the researchers, what will we do? Every day we check what is new in the archive. Archive database is the database of Cornell University. It's the official database that most of the researchers use. And every day you see new papers in cosmology, new papers in gravity, new papers in finance, in economics, whatever, any area. And then you keep update, You keep update. And then eventually you see an idea, I can use this in this part. I can use this method here. This is more or less how the researchers are operating. Okay. Thanks for the question. So now the current, the charge is measured by columns. These are the units of charge. 1 column, 2 columns, 3 columns, microcolumns, etc. 1 column is equal to 6.24 times 10 to the 18 electrons. So each column has a huge amount of electrons. Okay. The flow of coulombs per second is the units of electric current, ampere, the ampere. So in other words, the electricity, the current is the derivative in time of the electric charge. Derivative in time. I'm not so sure if the letters can be seen through the video, but because the live stream test, can we decrease the bright of this? What to decrease the bright of this screen? Somebody knows? You know how to do it?
Go to the search bar bottom there, and you type in settings.
Search bar in
Yeah.
settings.
Or just type brightness, I think.
I think there might be
yeah,
something
fine.
on the board, no, in this here, just to decrease the bright here.
It might not have a function key, but just type brightness in the search bar.
I cannot see it.
It's already
Right.
selected.
Right. Here. This. It's Wikipedia.
And maybe just display it.
Yeah. Because I think it's too bright for the. Or this video will be edited. I will cut things.
I
think
usually
you
it
have
should
to
be
go
here
into
somewhere.
advanced display settings at the bottom.
Oh. No. That's what it's usually here, I think.
It's usually here.
Yeah.
Rapid settings, advanced
It's like
display.
it's missing certain.
Or maybe it was directly here with this screen.
It's like a. It's like there's certain setting things that are not good.
Okay, thank you. Anyway, we tried. Okay. Anyway, let's continue. The point is that the current here, as I remarked, is the derivative of the charge with respect to time. So it's the number of charges, in average, will be the number of charges flowing in a given amount of time. And this is what we call current. Current. Now, obviously, when we transmit electricity from one point to the other, there is dissipation of energy. Okay, because part of that, the energy you invest for transmitter, for example, that's why the companies charge you electricity. Why do you think the companies charge electricity? The process is as follows. The water falls, well, it could be water or nuclear plant or whatever. If it's a nuclear plant, it's a gas expanding. If it's a hydroelectric, it's water falling. The water falls from somewhere here. It goes to a turbine. The turbine is here. The turbine moves, And later we will see that a change in magnetic field generates electricity. Normally it's AC, alternate electricity, it goes from one side to, and they transmit that to your house. But for transmitting that to your house, before they use something called transformers because they have to elevate the voltage. Later we'll see that when you elevate the voltage, you reduce the losses. That's why the cables, they have high voltage, but when they arrive to your house is where the electricity can be wasted and the voltage is lower and the amperage is higher. Later we will see that process, but this is where study engineering knows this process. Of course, I studied engineering first, so I know perfectly the process. Guys who study physics, purely physics, probably they don't know this process. They know that it's possible, but sometimes they don't care the application so much. No? So now, I must remark that if we have two charges, let's say two charges, I put a charge here, Q1, and I put another charge here, Q2, right? And I want to calculate the force that, for example, the force that charge one experience. Let's assume both of them are positively charged. Obviously, this will execute a force in this direction. It will be proportional or equal to, let's put it proportional to the product of the charges divided by the distance. This distance squared. And if you want to convert this proportionality in an equality, you have to put a constant, which is this constant K, which is already well defined. This constant is equal to this value. As you know, the distance is in meters and the force is in newtons. Something to remark is that, look at this equation. What does it look like? Like the law of gravity of Newton, right? Exactly. So for this coincidence, precisely because of this coincidence, many people in the past, they believe it that gravity and electricity could be unified in a very simple way. And many people try it, actually. Many people try it, but classically they could it by putting one more dimension, a fifth dimension, actually. Normally, the space-time is four-dimensional. They put a fifth dimension, and they could unify electricity and gravity classically. The problem is when quantum mechanics appeared, then everything fell. These are the famous Kaluza-Klein theories, which of course we will not see here in this class. Let's do an example. One example in this class is, let's calculate the force between two charges. This is the charge of an electron, minus 1.6 times 10 to the minus 19 coulombs. Let's calculate the force that two electrons separated by 1 millimeter field. So the distance is 1 millimeter is 1 times 10 to the minus 3 meters squared. K is the constant, is defined like this, and the charge is 1.6 times to the 10 to the minus 19, 10 is 2 electrons. When you calculate, look at the force. It's quite small. No? So, of course, this means that for feeling the force in between two materials due to electric charges, you need many, many electrons. And normally, as I said, there are many, many electrons. Usually at least 10 to the 23 or more electrons, usually in a space, in a cable or whatever. That 10 to the 23 comes from where? There's a number called Avogadro number. I don't know if you saw it in your school, but well, this is an animation. Well, I don't know. I don't think it's animated. But this is what happens when you put a positive charge and a negative charge next to each other. The electric field will go radially outside, but it will feel this is the source of electric field. This is the sink of the electric field. They have equal charge, so all the lines going out here, enter here. However, if I duplicate the charge here, if I put 2, half of the lines will go here, and half of the lines will go to the infinity. If I triplicate, 1/3 of the lines go here, 2/3 of the line goes to infinity. And so on. That's the issue. Now let's go to the phenomenon of electricity. I've seen this already. I don't have to repeat that part. This part we saw already. When you have these thunder lights, you have seen them, I think, are very scary. When you see these kind of thunder lights, what does it happen? Why people say, oh, switch off the mobile phones when you are walking below heavy rain, or don't stay below a tree or so? Because, of course, this is the phenomenon. The clouds start to be charged, positive, negative here. The Earth also has positive and negative charges. The air is neutral, macroscopically neutral, but locally it's polarized. Can polarize. The electric and positive and negative charges can be splitted somehow. So, of course, opposite charges attract, and this is what generates the electric discharge. And if there is a tree or a tower, metallic tower, the electricity will say, oh, better, I have a easier way to go there. So if there is a metallic tower and you start to touch it during rain, is the worst idea, the worst thing you can do. If you are in a car, don't touch the roof of the car during rain. It's better to stay inside the car. Actually, inside the car is safe. Even if a thunder light hit the car, most likely it will not reach you because you are seated not in metallic things normally. So it's like that. Later we will see. We are not here yet, but this is an electromagnetic wave. The electromagnetic waves move at the speed of light, but still we are not there. We are still, it's still too premature to talk about it, but you should know that electromagnetic waves contain electric and magnetic fields, oscillate, and they are transverse. They move perpendicular to the electric and magnetic field at the speed of light. Finally, we have magnets. The magnet has north and south pole. The lines of magnetic field are always close. And the electricity generates magnetism. Actually, you don't know, but when you have a magnet, for example, you have a magnet here with some poles, the lines of magnetic field do this. The north and south pole, and if north, south pole, and if I destroy this, I will obtain two magnets with their own north and south pole. In other words, there is no way to isolate a single magnetic charge. And these lines of magnetic field are generated by small currents. There are small, tiny currents in the material internally which generate this kind of magnetic. We will later see that how the electricity, the currents generate magnetic field, and vice versa. A change of an electric field generates magnetism. Change in time. So magnetic monopoles have not been observed. It's not like the electric charge. You have electric charge here, charge positively, negatively, whatever. We don't have magnetic charges. And if they exist, they are very heavy. They have a huge mass. theoretically, many people have predicted. Paul Dirac himself justified the quantization of the electric charge. It was only possible if there is magnetic monopole. Well, if magnetic monopole, we have not seen it, they have to be very heavy. Huge mass. Remember that when a particle has a huge mass, it lives less. It has less time for living. That's why many particles cannot be observed. Even the Higgs itself cannot be perceived freely because it decays quickly. And that's why they have to accelerate particles in the LHC, the Large Hadron Collider in CERN. Later, this is the principle of generator for electricity. Later, we will see that when this is a wire, there's a magnetic field in between. When this rotates, the flow of magnetic field changes in time. Because in some periods, this wire is facing the magnetic field perpendicularly, the plane of the wire, while in other moments, there is no flow through perpendicularly. So the flow changes from zero to non-zero to a maximum, etc. And this is what generates electricity. This is what generates electricity in your houses. So you can see how useful is physics and so on. Then let's do a parenthesis. I will summarize this part until now for you to have an idea. Let's stop the thing. For the moment, we have seen electricity, electromagnetism, but only the electricity part, no? Electric force, electric charge. The charge is quantized, quantized. This means that any charge is multiple integral of the charge of the electron. Now you can argue, but the quarks, they have charge and they have fractional charge of the electrons, but they are never free. I mean, any free charge comes quantized in terms of the electron charge. The Coulomb law, the force between two charges is K Q1, charge 2 divided the distance between the charge squared. And of course, as a vector, this goes radially. This means that if I have a charge here, positively charged, and I put a test particle here, positively charged, this particle will feel this force radially. And this resembles Newtonian law of gravity. And that's why many people in the past suspected some kind of unification, which failed by adding an extra dimension. Fifth dimension, Einstein himself supported that idea. That idea came from some other guys, but Einstein said, oh, it's a beautiful idea. But after it failed, somebody else demonstrated, oh, you are wrong because quantum mechanically this failed miserably or catastrophically, let's say. And then, but that's the nice thing of a science. People propose things, and sometimes most of the things we propose in physics are wrong. But this, you need to keep proposing things, keep proposing. Electricity, the electric current is summarized here. When you have a wire here with positive and negative charges everywhere. Normally, the negative charges are represented by the electrons, are the ones which move. Then if you apply a voltage, V1, V2, with voltage 1 larger than V2, the electric current will move from larger potential to a smaller potential. And this means that the electrons will move in the opposite direction. The electrons move very slow. They collide with the impurities and other atoms, etc. And this generates heat. But the electric field moves at the speed of light, and that's why we can perceive instantaneously, almost instantaneously, because it takes a finite amount of time. It will be calculate the speed of light 3 times 10 to the 8 meters per second, and estimate the time it takes for going here. It's almost nothing. It's very small. So that's why we can perceive the signals of the electric field quickly, but the electrons move very slowly. There are cases, there is a special case where the electrons move freely, is superconductors. It's a quantum phenomena which we will not study rigorously, in rigor, I mean. But maybe I will share with you some video about it, which I prepared. I will send you to your emails, but superconductivity is a phenomenon which happens in some materials when you decrease the temperature. So it comes out that there is a phase transition in that material which allows the electrons to flow as if there was nothing, freely. It's a perfect harmony between materials and electrons, and they flow without any resistance. And the current is just, if you keep the conditions, that low temperature, and the same conditions, then the electrons can flow forever, technically. I mean, the decrease of the current in time will be almost nothing. And the superconductors are important because they expel magnetic fields, and this is what the maglev in Shanghai, for example, use for keeping the trains floating in the air. It makes the train super fast. Some bullet trains are done by the paths. I mean, the lines of the train are done by superconductors, which have to be a very low temperature for keeping those conditions, and they expel the magnetic field. The train has some magnets, and they levitate. They move in the air, but you don't realize that they are moving in the air, and you are inside the train happy, but you don't know you're flying, at least a little bit more. Then, and it offers less resistance, no? Because there's no friction with the. So for the moment, we have seen this part. Later, after the break, because now it's time for break, we'll continue with electricity. There are things to see. The Gauss law, which is fundamental for calculating the electric field. How to calculate electric fields? What is the relation between electric field and force, electric force? And some minor problems. And after, subsequently, of course, we've gone to magnetism. I don't know if this class will be enough to cover the whole topic, but we will have another class anyway where we can do that. Then for the moment, let's go to break, and then that's it.